Thanks to Q2B for the invitation. Today I'm going to talk about quantum computing research activities at BMW Group, and specifically I will focus on material science research, and which I'm currently leading at BMW Group. So our QC team is based in New Technology and Innovation Department of BMW Group, where we focus on mainly three topics, research topics: AI and generative modeling, numerical simulations of physical process, and material designs and optimization. Each of these independently has very important use cases for BMW Group. For AI, example, generative design; for numerical simulations, structural analysis. And within material design and optimization, we have identified various use cases, and some of them are listed in this list. And I'm going to give you a deeper dive into our use case for lithium-ion batteries and hydrogen fuel cell application. Yeah, before we go into that, I would like to show you the new materials development process. How do we do that? So, the numerical simulations, it provides a filter between an initial idea generation stage and where you could potentially identify new materials to discover that you could have in millions to start with, and the final product where you synthesize in the lab, which could be expensive and also time consuming and human resource. It takes lots of good scientists to work in the lab. So what we would like to do is to know the process, how to filter well the materials. And better we know, we will minimize this trial and error that we do in doing like experiments. So, for example, the classical, very near exact simulations, they don't really scale well for the larger systems. And those conventional larger methods, like that can do like larger system but approximate, they're not really good enough for like highly correlated system, which is the case for the battery active materials. Also, hydrogen fuel cell catalysis reactions, and various use cases we look into BMW Group. So therefore, we think that quantum computing can enhance some of those processes that we are looking into. And for example, here where we have a list of tasks we do together with academic partners, quantum solution provider, and also in-house in this regard. So why do we need like various processes, the classical methods, also like new quantum computing methods? The processes we are looking into for, let's say, battery cell chemistry is highly complex, multi-physics. And I'm going to give you a picture for battery cell simulations. So what's important for battery cells that we would like to know how the battery cell performs in their operational life. For example, over time, the battery cells like power density and energy storage will reduce due to degradation processes, and that we would like to understand it better. In our battery competence center in Munich, BMW don't make the battery cell itself, but we would like to know the performance of batteries while it's in operation. In order to do that, one would like to do simulation at different length scale. So for example, in this slide, you see that the length scale is like, in terms of molecules, is angstrom, coming up to like nanometer, continuum physics, up to system dynamics. So this battery pack, which goes into the car, where you have like control for the electric, for the thermal parameters, when the battery gets overcharged, how you cool it, and everything. And in between, you have simulations done at continuum physics level. So at this stage, what you do is like you model the battery cell in terms of particles, more like physics, 2D particle, 3D particle, and based on that, you could actually look into some of the thermal or chemical events of the battery cells during operation. And we believe, and it's very evident, that some of these simulations requires input from what's happening at atomistic level. Some of the chemical reactions, so there are various chemical reactions that happens during cells being in use. And better we have the simulations done at atomistic level, more parameters, more exact parameters that goes into the continuum level of simulations, then it will enhance the continuum levels results. And how do we go from atomistic simulation to bringing up to continuum? So one could do, first of all, like very small scale, very high accurate methods. Then, by parameterizing some of these properties, molecular properties, and bringing up to continuum physics level as input to enhance this continuum physics level of simulations. I can give you one example. So for example, once you synthesize, let's say, battery cell, so you have lithium as active material, which you can think is in terms of micrometer length, and you have outer cell, that's battery is packed. Even due to like a small gap in micrometer, or due to mechanical forces, you might think of like some leakage that battery can have. That you can also simulate from the new continuum level, but you will benefit, one would benefit, or we will benefit while doing simulation in the competence center, that we know that how the crystals in lithium, which is again not stacked periodically in terms of chemistry, you have different phases, you have different orientations, that how they, let's say, due to mechanical forces, how they collide with each other, what are the forces that goes into different phases of lithium, and if you can simulate those at atomistic or even bigger periodic level, and then bring those results as parameters for doing this continuum level of simulations, and then you can actually improve, like in some thermal events or in some due to some electric event, how they would perform. And this is something we actually would like to do simulations together with our battery competence centers. So we would have to have different KPIs for this sort of simulations, that what key parameters we would like to do in terms of simulation and the results. Yeah, and so then next question comes, how do these problems translate to our roadmap for doing quantum computing? So what I'm going to show you that a roadmap, a very rough roadmap, which includes both classical, as we still need lots of classical methods, and quantum enhanced solution. So in this slide, what you see is like in the green dot, it represents the classical quantum chemistry methods. And in the blue, we have listed some of the quantum solutions that includes, for example, DMET and Q-solver. So this is one of the examples you still apply density matrix embedding. So in order to avoid the larger system, you bring the problem smaller by doing some sort of embedding, and then you apply together with quantum solution to enhance some of the results. And this, for example, in this case, we are looking into, let's say, active materials, electrolytes, interface, and battery. The battery management systems, so in one of those three slides, we had these three unique circles. So we would know that, like, if we make some certain development in AI or numerical simulations, we could also benefit that in material research development. And in this case, for example, this is not exactly a molecular level simulation or anything. So the battery management system is almost a complex process that you just need to have lots of optimization. And there one could also employ our numerical simulations technique that we are doing within our center. In terms of pursuing partnership, we are also participating into QTech consortia in Germany. And for example, the DMET project is also sponsored at TUM as a PhD student. And together, very recently, our colleagues in Japan, they also became part of Q-Park system brought to us by Kunasis. And for embedding and density, and one of the most important, DFT is a workhorse for the classical simulation, but still we could also look into enhancing DFT exchange correlation functional. And this could be taken, one could take approach from quantum machine learning, or even go more fundamental to look into exchange correlation property and to see how physics-wise we can improve it. So this is something we are also planning to look into it. Together with Continuum, we also participate for research, for example, in hydrogen fuel cell. So this roadmap we have could also easily well translated to other chemical problems or other chemical applications we are looking into. And I'm going to give you our collaborative work together with Continuum in terms of hydrogen fuel cell application. So first of all, why we would like to look into hydrogen fuel cell. So we do have a bigger picture that if you have hydrogen fuel cell based car or any energy or any such processes, you would like to reduce the carbon emission and at most, let's say, zero carbon emission in the bigger picture. In the whole fuel cell ecosystem, there are various stages, but here we would like to particularly focus on one very key important catalytic reaction that actually enhances this fuel cell efficiency, and that is oxygen reduction reaction. So this is a project we have started with Continuum in March 2021. This is phase 1, where we look into very simple system. So now here you see lots of layer of platinum. So in the first phase, we only took one single crystal. We put oxygen, and then we look into dissociation pathways. And from that studies, what we learn, using quantum methods, one calculated activation energy. So activation energy is something that before a reaction that goes like from one A to B, it goes through a pathway C, and you want to see that how this C energy is computed compared to the reference. And in these studies, we saw that our results with platinum and platinum surfaces matches with experimental results. But still, in order to have more realistic system, we would like to have a system that incorporates most of the correlation effects, most of the site localization effects that I'm gonna show you here. So in terms of accuracy, we would like to do simulation where we can have accurate energetics that will draw. If we have to do some kinetics, then we would have energetics input that's more and more accurate or more closer to experiments. We would also need to have a scalable solution, for example. So if we do classical simulation, classical embedding methods with very large active space, that will require lots of memory. So we would also like to avoid it. So we would also need to look into some sort of embedding method where we can reduce the system size, but still capture most of the correlation. And this is where we also look into embedding based, or like have a very small active space for even a bigger problem to solve for the correlation energy. The industry relevance, so this is phase 2 project where Airbus, Aerostat, and Continuum, we are all working together. And the relevance of the industry is that input came from Airbus and also BMW, Aerostat, that most of this catalytic reaction are still driven with platinum, or like platinum, which is very expensive. There are experiments where one would like to say that to reduce the platinum, what one could do is to keep the layer of platinum on top and then change some of the layers with cobalt, nickel, maybe have some of the different configuration in the edge crystal to see that the catalytic process are improved and with less amount of platinum. And this would mean that we would still need to have very high accurate methods. We would still need to capture lots of electron correlation for the energetics calculations. And that we do in this schematic. So this is the schematic, this is this work done at Continuum. Thanks to Kono, Mihal in this audience, Davide, and also other Continuum team members who has done some of the experiments and the emulators. So I will give you a brief idea. So for example, one could start with this full systems at DFT and Hartree-Fock level because some of the geometry is still done at classical level. What you look into local area of the reaction. So you don't really look into everything. You have some sort of localization. You would like to see also the fragments, and that would mean that maybe some effects are from the top layer, some are bottom layer, some from different region. So you also make fragment choice. Then you choose active space. You make a VQE state for quantum state. You do some sort of emulate with emulator, and then we also perform some of the hardware experiments that I'm going to show you. So here is example of our results. So for example, in this case, we did some numerical calculation where you see three different types of fragments, all done with like 5 surface. And you have different number of platinum coming from different layers. And you see that we did this convergence studies based on the overlap of the orbitals with the atomic basis. So this is a little bit chemistry there. And we saw that we could find a very good convergence for all 3. But based on this, we chose one of the system that actually captures most of the chemistry. How much time do you have? Okay, yeah. So I go quickly. And so here I show the results from the classical methods, comparison of classical with VQE, and comparison of classical with VQE, and with a correction of PT2 for capturing dynamic correlation. So in one of these reaction, we would like to have, there are 2 products. One is called cis, and there's trans. Trans is in the green, and cis. And comparing these 2 classical, DFT and Hartree-Fock, we would see that Hartree-Fock are giving a different trend for the product state. we did VQE, and we see that the trend is still wrong with compared to DFT, but the gap, energy gap improved. So coming from this, what we see that there is still some correlation missing. And if you add some of the correlation using PT2, then you see the improvement or a nearly exact trend as DFT for these results. There are some caveats, or there are some features that I would like to mention. Activation energy for these two remains the similar trend, but here we have underestimation of activation energy. Yeah, and this is very important slide just to show the upper level like I would say that's progress, that we also did emulation. These results at emulator level and also hardware results. And both actually matches very, very close to each other. So that would mean that like if we progress with hardware so emulator and hardware giving same results, it promises that with improvement in hardware, we would be actually able to do some of the chemical simulation with hardware, quantum hardware. And this is to show those. Yeah, I come to final slides. So to conclude, what we understand that in order to solve some of the problems, we would require the field expertise from the problem we are looking into. So those field expertise we also require people who could do lots of quantum computing, quantum algorithms, collaborating with them together, and also taking account of our business unit needs, what kind of problem they would like to solve, talk with them, formalize the problem in a way that it can be tackled using quantum algorithms. So we would benefit from this new tool or new development in quantum algorithms. Yeah, and thanks to the team of Continuum, our BMW colleagues in Munich, and to everyone. Yeah, and to add, some of our colleagues are also talking in automotive sector, so you could also go tomorrow and listen more about other BMW use cases, mostly optimizations, more closely to the production processes, and one of those use cases. Thanks a lot. I hope that's it. Yeah.
So two quick questions. You mentioned one, looking at potentially replacing some of the exchange correlation functionals with parts of, I guess, the QPU as the contributor, or making the contributions to the exchange correlation functional.
Yep.
Yeah, can you talk to like what kinds of functionals do you plan on either replacing or augmenting? Like, are we talking hybrid functionals beyond? Are we talking about GGA functionals that you add corrections to?
So, I mean, I would start with like hybrid functional anyhow. So if you go on GCA, we don't have exchange. So for any battery active materials, you would like to have the exchange correlation. I mean, without hardware exchange, there's hardly any improvement. So we look into DFT problems at two scale. One is to benefit from some machine learning approaches to improve the quantum, like DFT. I mean, that could be ML, QML, that we apply what machine learning can learn from data, good results. But the second thing is DFT functional itself is a very fundamental problem that we would like to reformulate with some of the constraints that's already been used to optimize the classical DFT that we would also like to do with the quantum.
Awesome. And that brings me, great answer, thank you. That brings me to my second question, which is on the use of VQE. So, you know, if you go down the route that you just described, one concern that I see with a lot of people who are trying this is that, you know, pure states and Hamiltonians and finding the ground state are obviously important, but nature has more complex states than just finding the ground state, right? You have pure, mixtures, mixed states, and so on, excited states. So do you have any plans on tackling those problems?
Yes, it depends on what kind of chemical problems we are looking into. In some of the cases, excited states are very important. Some of the photophysical process, you would have to have very accurate excited states. But some of the chemistries are still ground state. And in some of the chemistry, you would like to see the energy differences. And that would mean that even if you could do single point energy calculation for every species involved in a reaction, that's going to give you a better reaction estimate. So ideally, there are two approaches. To design new materials, you would like to have many things. To optimize chemical reactions, you would also like to have various tools. So I would say that for excited states method, there are a state-specific BQU that's being developed, but that's just a start of the tools.